Hello boys and girls. So in the next video I want to talk about topoi of sets inside the von Neumann hierarchy, and I will discuss when certain mathematical objects of standard interest show up and whether or not they are represented as objects of this nice category. And when we talk about mathematical objects, in set theory, coding plays quite a role, because depending on how you specify the structure of interest, certain properties that are not seen in the native theory of those objects. So, for example, if I'm talking about real numbers, I'm just interested in the real numbers or sets of real numbers. I'm not interested in set theoretical coding. These aspects are invisible, and what's important for seeing when certain objects are part of some of the categories we will talk about, the rank plays a particular role, and also the cardinality. So in this video, I do separately talk just about these sort of coding aspects, and I will explain it using not even just set theory, but codings of objects in arithmetic and set theory, and do some comparison, and then you learn some about maybe even some efficient codings that you didn't know about. So I scroll up. This is the text that we will talk about next time, but I just scroll up because here at the start is this the bit that is relevant for coding. I start out here talking about second order arithmetic. So here we have quantifiers over the natural numbers, that's the intended model, and we also have quantifiers over sets of natural numbers, which can be understood also then as like predicates of natural numbers, right? You say all the even numbers represent the predicate of being even, and you have quantifiers for this here, but you do not have quantifiers over the Cartesian space. There's no like uncountable objects here in the intended model of these arithmetic theories. And here what you see on screen here is one possible coding of some Cauchy real numbers or representations thereof in second order arithmetic. So let me just step through this. I will show you this and some other codings of real numbers in second order arithmetic, and then we'll see where the differences lie that are of interest to us here. So you can represent a real as a Cauchy sequence of rationals in the set theoretical model, where you use extensionality of set theory as equality. You would then consider an equivalence class, but here we look at individual sequences just representing these reals. And to represent some generic rational number, it has a sign and it has a numerator, denominator. You can do this in terms just of natural numbers. And so you get this expression representing a rational, and you want many of those, so you also have an index I, which also happens to be a natural numbers. So this sequence is coded as a quadruple of natural numbers, right? You have the index, and you can then package all these quadruples with unique index. You just put them into a subset of n to the 4, and then it represents one of these sequences. And if it's a Cauchy sequence, meaning if it converges in the nicest sense to a point, then you have that representing a real number. You can also take this n to the 4 and do further coding. Either you use pairing functions, or you do make use of the fundamental theorem of arithmetic. Just encode these 4 numbers as the exponents of particular primes, and then if I hand you one natural number, you can look what are the prime factors and what are the powers, and then you have your correspondence to these two quadruples. And here, so for example, here is a set SE. The E represents the Euler number of the natural numbers. Here are the first few natural numbers, and if you would do the factorization of these into this here, then you would find out that these numbers here indeed represent the first 4 of these sums. And of course, this sum if you take the limit, goes to the e to the 1, so the Euler number, and therefore it represents this real. And in this way you have like this correspondence between a subset of n with one real, or if you take real to mean the equivalence class in set theory, then one representative of this. But you know, in reverse math or whatever, you use literally these sequences, maybe coded differently, maybe converging faster. You know, you can tweak whatever sequences you want to do, but you just use subsets, some encoding of the reals via some subsets. And I want to point out that the size, the cardinality of this real number, right? The individual, just a simple real number, SE, is a subset of the natural numbers. And so the cardinality of this real number is countable infinity. And something similar happens if you do a Dedekind real encoding. So here you take the rationals, which are also countable, which you can also code as natural numbers, and you have this you know, left side, and you represent the same Euler number but completely different. But since this is literally a subset of the rational numbers, also this, oops, here I have the letters wrong. One of those should be I think this should be an L, is also countable. And then of course you have the Cauchy reals as equivalence classes now in set theory. And so here one Cauchy real contains all these sequences which look similar in the sense that they converge to the same point, right? But you can always take any binary sequence of natural you know, 0 or 1. This an represents some sequence where all coefficients are 0 and 1, and divide it. You get something which goes to 0, and of course there are 2 to the n many of these sequences, so there's uncountably many of these sequences, and you can always take any Cauchy real number representation and add this noise. And so this means that in this representation, or in set theory with the Cauchy reals, the cardinality of one single real number is different, right? So Dedekind and Cauchy equivalence classes, in the way I have just defined them, these objects, just depending on, you know, on the coding, have each a different cardinality. They have different width as objects in set theory, even if the structure, you know, after you define the addition, multiplication on these sets, even if this is isomorphic, the objects have different aspects that just stem from the coding and that are not relevant for the arithmetic of the real numbers, or even the topology of the real numbers. Okay, and so we have discussed here numbers. I will also now discuss tuples and function spaces. So for this we need the von Neumann natural numbers. I just point out I have a video on this here. So you know, the von Neumann natural numbers are one representation of the natural numbers, and you can also then define addition on them and multiplication. I don't think we will use much of this here, but basically you say the empty set represents a 0, and then each other set represents the finite set that contains all the numbers before them. These are the countable von Neumann ordinals. And the Kuratowski ordered pair is this definition, right? So a pair is, you can take any model of the pair, just needs to fulfill that it has the categorical properties of you being able to uniquely project out the left and right component. And so you have this thing. And what is relevant for us here, I mean, there's many codings of natural numbers. This is like one often used one. It has the property that if A has some rank, right, some depth, right? So for example, the number 0 has 0 rank. The number 3 happens to have 3 rank because, you know, you include deeper and deeper objects. If you form the pair of two sets and A has some rank, then the pair here has a deeper rank than just this A. If A and B have the same rank, then it's just whatever rank they have plus 2. And in this way, you already see that just from the coding, like however you represent the objects, you get a deeper rank. And you know, this definition having been looked at, let's look at the exponentiation, right? So we already had the von Neumann naturals. You can consider the function space, which is a collection of certain subsets, which has like as input entry, in this case, this set, and as output entry, this set, right? And so any function in the standard definition of a function in set theory is a subset of the this set of pairs, right? So for example, one function might map the number 0 to the number 3, and therefore a member of the function will be the tuple, which has 0 in the left entry and 3 to the right. And so if you do this, then it turns out that the cardinality of this function space, the number of functions, is again countable, and this number is exactly the same cardinality as if you just build this set. And so now, what is actually the rank of the function space? Well, you have the rank of the set x and the rank of the set y, and the function space is a collection of like a collection of sets that hold tuples, and then you can do the math and you find, okay, if I build a function space, then I actually bump the rank by 4, right? So you can think this through. But then again, there's also another way in which you can consider this sort of exponentiation operation, which also gives you a set that has cardinality, which represents the correct correct numbers to represent the arithmetic of natural numbers with sets. And what you do is you just chain the codomain together with Cartesian pairs. You do this thing, right? You take 5, cross 5, and you cross 5. This thing also has cardinality 125 in this case for this example, and in this case it also bumped it by 4. But the thing is that if you have a function space and you have some x and some y here, and you construct a space of all functions which are sets of tuples, then the rank only ever goes up by +4 over the largest set that you used, versus if you do long chains, long finite chains of these Cartesian products, then if you, for example, if you do 5 to the power of 17, then these objects are nested tuples, right? So this thing is just a tuple where the first entry is another tuple, and so on. And we saw already that building one tuple gives you a depth of +2. And so this sort of operation gives you a very quickly very deep sets. And so even if you represent the same sort of thing that you want to get at, in this case we just want to get the right multiplication rules as judged by having the correct finite cardinalities, then coding makes a difference here. And the whole reason why I got into making this video in the first place is I was writing the script for the category of sets in the von Neumann hierarchy, and I was talking about the Cartesian space, the real numbers to the n, r to the n. And at one point I noted that I was using different codings. Like on the one hand, I was using the coding with the tuples, which is sort of the natural thing. If you think of r to the n, if you think r to the 3, you think of 3 tuples. If you think of the elements as these vectors which have 3 components, but you can also encode it as this function space, right? This collection of functions where the domain is just a 3-element set, and the output are some real numbers. You code the same sort of objects, but in the function space definition you just have a much lower rank, and therefore these coding pop up earlier in the von Neumann hierarchy. This is something that you will see in the next video, but it just means that if you want to ask, at which stage of the von Neumann hierarchy does this mathematical object of interest pop up, then you run into questions of coding, because the most natural coding might not be super suitable if you want to have this set enter at a low level. Okay, and so finally I want to talk about ordinals themselves in arithmetic versus in set theory, their representations and order types. I have these two, which I think very nice video, in particular the first one. I have never seen this done on YouTube anywhere. I mean, it is in some papers, but this is some very like recursive computable stuff. Go check it out. Okay, so I will do the example of omega squared very explicitly here, coded in taking the order type of this ordinal and showing you how this is coded in, for example, piano arithmetic. So this picture here is just so you have like an intuition. The order type that I will define, omega squared, can be encoded with this set of tuples where all the entries are just this natural number. So this is just a set of pairs. This is a set bracket, and of course they don't have like a necessarily, the sets don't have a like a natural order that is placed on them, but I like just for intuition stack them up here like this matrix. And of course you have, for example, if you fix the first entry to 0, then you have here a sequence from 0, 1, 2, 3. This is like one sequence of omega itself, of the natural numbers itself. So you have like one copy of the natural numbers, and they have an order. But if you just look at the second component, 0 is smaller than 1, 1 is smaller than 4, and so on and so forth. But then you have also this jump to the next row where I change the first component, right? And the order type for omega squared, for the ordinal or omega squared basically, can be coded easily in piano arithmetic by having some bijection between the natural numbers and the pairs of natural numbers, and then defining the ordering or that corresponds to this order type in this sort of way. So you say, firstly, if they are on the same level, then you just use the natural numbers order, which I represent here by going left or right. And otherwise, the entries which come with higher rows, the one which are later in the down direction, they are bigger with respect to this order. And then there's this very simple definition. And in this way, I encode an order in piano arithmetic, which has, the is smaller than symbol, but I encode another type of ordering, which has this jump, right? So here in this direction you go with the successors, but in this direction you have to do these jumps. And then of course, I've already represented this here as this set of tuples. You can also then formally define this. And since this is representing omega squared, there are some other order types which are smaller, and smaller in the set theoretical coding then means that they are included in this order itself. So I give you some examples. Of course, you have, for example, the ordering omega plus 7, right? In the Neumann coding, this then corresponds with this set theoretical countable ordinal omega plus 7, where first you have this all these copies of the natural numbers, and then you allow yourself one jump and still go to the element 7 here, right? So this is basically just one jump, and this is the set that you want to impose this ordering on, and you do not care. You can also go further, right? So here I also write down omega times 3. So this is like the ordering of the first 3 rows, and nothing else is of importance to you. These are all order types which are here in my visualization already included, right? It's clear that omega times 3 is like you intuit what the ordering is. It just means the induced order from this even bigger omega squared, just restricted to the first 3 rows. And the thing is, in piano arithmetic, you cannot just do omega squared. You can also code very easily omega cubed. So you imagine this as a sort of tensor which comes out of the screen. And you can imagine omega to the power of n as well. And you can encode even more complicated things by going away from just n tuples, but having the collection of all lists, and you can encode this. This is really what this is about. You have like a fairly wild amount of lists, trees or whatnot, that you can still encode and just use piano arithmetic and define an order on it. The result, of course, is that you can then do not just this squaring, cubing to the power of n, but you can also encode to the omega. This is what I do in the video, in the other video. But then you can also take another omega. So you have omega to the omega to the omega, and you can encode objects in piano arithmetic and define still an order on this. And you can do this a finite amount of times here, and so on and so forth. Okay, and then if you have a stronger theory, you can do even more wilder objects and define wilder order types on them. In piano arithmetic, you have to stay under what is called epsilon naught. This is then the proof theoretic ordinal of piano arithmetic. First order piano arithmetic can not do any more well-ordered orderings. But then if you have a stronger theory, it goes up. The countable ordinals pretty much correspond to certain weak theories, or weaker than Zermelo-Fraenkel theory. And then, of course, once you go to Zermelo-Fraenkel theory, you get even to uncountable ordinals, and in the wildest distances, let's say, of orderings. I don't know, I don't want to use the word size because I don't want to conflate it with cardinalities here, but you know what I mean. You can go further and further out, and it gets really crazy. You can take omega to like omega 7 here. This is a certain uncountable ordinal, and then you can do to the power of uncountable ordinal. You cannot even imagine what kind of objects you need to encode this, but basically it's all the weirdo axioms that we will encounter in the next video. Okay, and then finally, we have seen that the order types, the orders are encoded here with this very simple language of piano arithmetic. First order piano arithmetic, you can do omega to the power of 2, and you can even go further. But of course, in set theory, you can also encode the same sort of order by jumping up in rank, like going up in rank in successor operations and representing the jumps. But in this previous example was like jumping from row to row. But this jump is basically this taking these infinite unions and going to this larger and larger sets. Okay, so here I define the successor operation, and you can see this adds rank plus 1 to any x. And you can do this finite amount of times, and then the finite for normal ordinals that we already saw in this video are obtained by doing an iteration of this. Here I tried to get this in with the notation. So here you see the normal n, and then here where I say do it n times, I do math m, so that you see this is the phenomenal ordinal, this is this set, and this is how many times you do it. And you can go wild with coding and make this clean, but here I'm considering this just a set, and here the meta-theoretical and operations, and you will have to like do all the recursion axioms to make this work yourself. I do not talk about the set theory axioms here. Okay, and so here we know how to do finite sets, of course. This is the bottom-up constructive part of set theory. And then we postulate that we can go beyond that. There shall be this object which contains an unending amount of other sets, omega. We can then isolate it with the axiom of separation. It happens to fulfill this sort of property. And then we can, with the axiom of replacement, which a large part of the next video will be about, do this fancy big unions. And for example, omega just happens to be the union of all the finite ordinals which we know to construct. and omega, which we postulate, ends up fulfilling this. And then we can define arithmetic on this, and you see that here. And now what I wanted to get at is, we saw already before, we had omega times 3, right? Which was the first 3 rows of this countable infinite rows. And here so previously I talked about the jump from the first row to the second row, and then from the second row to the third row, right? And all these objects together are be used as coding for this order type omega times 3. And now we know how to do a successor. We know basically in this image, maybe I'll show it to you again. So we know how we go in this direction. This is taking successor, and this jump here for this very small countable ordinal is done by saying, okay, now we just go to infinity, we take all of this, and once we have it, we are at a new object, which is the start of the next row, basically. So this is the same order type is encoded now with ranks, where the successor is jumping up once, and the jumping between to something completely new is encoded by taking this infinite union. And if you do this kind of thing, like we have already done it once with the axiom that postulates the existence of the natural number. So this is omega. If we do this 2 times more, we end up with omega times 3. And with the replacement axiom easily, but this is we are all at so small ordinals that we don't have to do too much there. But by taking this infinite union twice more, we also end up at a representation of the order type in terms of rank, but we've now encoded with these sets. Okay, so I'm talking a little bit in circles, but I hope you get the definitions just as they are on the screen. Okay, and so in this way, we can, once we have replacement, we can start this process of going up and up and up. And the thing is that, this is a spoiler for the next video already, we will look at the von Neumann universes where we do something similar, except there's also the power operation will be involved. Otherwise, it is basically the same as the constructions of these von Neumann ordinals, except we take this fancy operation, the power operation, and we generate the V levels, the levels of the von Neumann hierarchy that are indexed by an ordinal. Sort of the point of the next video will be to see that it's clear where certain objects of interest pop up, and they pop up relatively low. So these examples like omega times 3 that I talked about here are countable ordinals. They're not even uncountable ordinals, and even the first very low ones. And the funny thing is that to get a set theoretical universe at a topos of sets in which we have differential geometry and all this, we do not really have to go further than to a universe which is indexed by this small countable ordinal. And the funny thing is that this universe does not even contain that many ordinals, because, as I said before, we will do this next week, but to make this taking the union formal, you see that you have to do this sort of taking the image of a defined functional predicate step. This is where the replacement axiom comes in. And so you end up with, for example, V omega times 3, which will be a topos and a model of Zermelo's set theory, without the Frankel, without the replacement. And it has crazy mathematical objects, all your mom dreams of. I used this example before, so you can do Fourier transforms, all these kind of objects, the practical objects of the engineering world, and even the physics world, like categories of Hilbert spaces are there. But this thing doesn't even have the ordinal omega times 3, which is kind of funny, right? Of course, you can talk about these encodings. This theory is strong enough to encode the ordinal types certainly that piano arithmetic could encode, but it does not have the same ordinals encoded in terms of rank of its objects. Okay, so I will not draw this further out. I hope this was somehow informative, and we will make use of all of this in the next video. Take care.